Greetings, this is Mr. Thompson with the first in a series of video lessons for the calculus book, Calculus Concepts and Applications, for the upcoming calculus class. Now, this is one of my first times using this new software, so hopefully things go smoothly. Otherwise, let's go ahead and get started. So, Chapter 1, Part 1, the concept of instantaneous rate. Now, instantaneous rate is pretty much the purpose of calculus. Okay, calculating rate of change when the rate is having an acceleration done to it, which means it's no longer linear. First example the book gives talks about a automatic door opening and closing. Now, the door would open much quicker than it would close, so it does not slam. That's the nature of the automatic doors. So it opens up quickly, comes to a stop, then closes quickly, then slows down so it closes smoothly. So we have this idea where the speed is going to go up, 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 comes to a stop, and then closes really quickly, and then smooths out. All right? And that's actually pretty much the first graph we look at. So, to get us started, we start with our first example, where it says, suppose that a door is pushed open at time t equals 0 seconds, and the door closes at time t equals 7 seconds. And then it gives us the equation, the degrees that the door is open equals 200 t times 2 to the negative t for 0 seconds to 7 seconds. Now, it also has a graph in the book. It looks pretty much like this. I've already pre-plugged into a graphing calculator. So if we look at y equals 200x plus 2 to the negative x, I have set my window to match the window in the book. And here we have our graph. And that is the graph that we're going to utilize. Now, the question in this example wants to know how fast is the door moving at the instant when t equals 1 second. So that would be right about there. Now, if we plug it in and solve, that's not going to give us speed. That's going to give us the degrees the door is open. So we need to do a couple steps to solve for the actual speed. Now, what we want to do is look at the difference of how much the door is open between two different time periods to determine speed. So, the book tells us to start with using t equals 1 second, which is the goal, and compare that to t equals 1.1 second. So exactly 0.1 seconds later, how much more open is the door? So, what we're going to do is plug in 1 and 1.1 into our equation, just standard plug and chug, which I already have typed in here, which you will see. 200 times 1 times 2 to the negative 1 equaled 100. So, our degrees at time 1 equals 100 degrees. Now, you'll see this function notation a lot in calculus, so you got to get used to it. d of 1, which means degrees at 1 second equals 100. And then we have d of 1.1 equals, let's bring back the calculator, 102.6336291. Let's go out to 3 decimal places, 634. 103.634. Now, to get us the speed, we want to know the rate of change between these 2 points, the point 1, 100 and the point 1.1, 103.634. Well, it's the standard slope equation. Across the top, I'm going to put 103.634 minus 100. Across the bottom, 1.1 minus 1 gives us a slope of 3.634 degrees over 0.1 seconds. Now, that's pretty much good enough. However, degrees per 0.1 seconds isn't that helpful. So let's go one more step and convert that to over 1 second. So let me rewrite what I have. 3.634 degrees over 0.1 seconds. I'm going to multiply both the top and the bottom by 10. That gives me 1 second on the bottom and 36.34 degrees on top. So our door is moving at 36.34 degrees per second. Seems kind of fast, but that is what it is. Oh, did I make a... I did. I messed up. That's not a 3, that's a 2. So I'm going to go back and change that. Everywhere it shows up, it's not going to change our answer that much. I thought that seemed weird for a second. Shows up a lot. I apologize for that. That should be a 2 in all those instances. So I'm going to come back and change it up. I'll put it in red so we can more easily see that that got changed. That's a 2, a 2, a 2, 2, 2, and a 2. Alright, much better. Now, our answer isn't very exact. Calculus, if we're doing true calculus, would give us an exact answer for the speed at that instant. This is the speed over 1/10 of a second. An instant is not 1/10 of a second. An instant is an instant. So what we want to do is maybe change this up so we're not calculating from 1 to 1.1. So let's try a different setup. So I'm going to get to a new screen here. Let's take a look at what about from t equals 1 to t equals 1.01. Let's see how that changes things up. Now, we still know the degrees at time, time 1 equals 100. However, what is the degrees at time 1.01? Well, it's not too hard. There's a neat trick with the calculator to bring up what was last done. So second, enter. And now I'm going to enter an extra decimal point in each of these 1.1s. And see what we get. 100.3023. That's much smaller than 102. So 100 point, and I don't want to mess it up this time. 30, let's go 302. Now, I'm going to do the same calculation across the top. 100.302 minus 100 over 1.01 minus 1. We get 0.302 over 0.01. Now that's 0.01 seconds, so I'm going to multiply top and the bottom by 100. This gets me, on the top, 30.2 degrees over 1 second. Now, let's compare that 30.2 degrees with our last answer. 30.2 degrees is different than 26.34. It's more. Now, what we just did is an answer that's going to be more exact. Now, it's close to what we just had, but this one's more exact. This is what we want. Now, what happens if we jump way ahead? Now, the book keeps on going, 1.001, 1.0001, and keeps on going. Let's jump all the way to the last one in the book, which is 1.12345 zeros. D of 2, 3, 4, 5 equals, let's plug it into our calculator. I need to enter 4 more zeros. Oops. Let's try to not mess up on this one. Need to enter 1 more. And on the bottom. And we get, man, it's a lot different. I gotta go a lot farther out than the third decimal place. 100 point, let me bring it back, 0.0000307. I'm gonna do it all. 0.0000307. 4 zeros and then a 307. Now, let's do our math. Now, you should be noticing that we're only subtracting the 100 off, which means we're left with a decimal each time. So I'm just going to go ahead and put that on top. We have 0.0000307 over 0.00001. Now, to get rid of all these decimals in the bottom and make it 1 second, I need to multiply, let's see, 10, 100, 1,000, 10,000, 100,000, 1 million. I got to move that decimal 1, 2, 3, 4, 5, 6 times, so multiply by a million. Just forgot the 1. Now, all that's doing is moving the decimal, so let me go ahead and show that movement. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So as you can see, hopefully, we now have 30.7 degrees over 1 second. Pretty close to 30.2, but this answer is even more exact. Now, we had a much different change from 1.1 to 1.01. Okay, 26.34 to 30.2 is a pretty big jump, but this is not a very big jump. And we even went this far out. The farther out we go, the smaller it's going to change, but the closer it's going to get to an exact. And the exact is the limit, which you should have talked about limits at some point. And so we're going to look into that. Now, calculus would get us the exact without having to do all this. And that's the value of calculus. Now, before we get into that, though, let's continue practicing this. This will be the end of this video, and then I will go into a couple of examples from the homework set for this chapter.